Hello everyone and welcome back to the second part of our discussion on linking and relocating loaders. Earlier in part 1 of our discussion, we have examined the basic concepts involved in program linking and we have discussed the issues of program linking from assembler's perspective. Specifically, we had considered more complex example of external references between programs, namely A, Program B, and Program C, and we have seen how the assembler generates the object programs for each of these control sections, program A, B, and C, with modification record to instruct to the loader uh, any information that is required for program linking. In today's discussion, I will be focusing exclusively on the functionalities of linking and relocating loader. And loaders of this kind are typically found on machines where relative addressing makes relocation unnecessary for majority of the instructions. We assume that modification records are used for relocation as well as linking, so that linking and relocation functions are accomplished using the same mechanism. Input to a linking and relocating loader consists of set of object programs or set of control sections that are to be linked together. For example, in the example that we had considered, there were three programs, namely program A, program B, and program C. So now if these three programs are to be linked together, then the object programs corresponding to program A, program B, and program C should be given as an input to the linking and relocating loader. It is common for a control section to make an external reference to a symbol whose definition doesn't appear until later in the input stream. So required linking cannot be performed until address is assigned to external symbol involved or until the later control section is read. Thus, linking loaders perform two passes over the input, and during pass 1 it assigns addresses to all external symbols by creating external symbol table, and during the pass 2 it performs the actual loading, relocation, and linking by employing the external symbol table that was created during pass 1. So the main data structure employed by the linking and relocating loader is the external symbol table, which is analogous to the symbol table that is used by assembler in the assembling process. So as I mentioned, external symbol table is used to store the name and address of each external symbol in the set of control sections being loaded. Further, external symbol table also indicates in which control section an external symbol is defined. Typically, hashed organization is used for external symbol table. In linking process, two important variables used are program address or program load address and the control section address. Program address is the beginning address in the memory where the linked program is to be loaded. And this value is supplied to the loader by the operating system. So program address indicates the starting address in the memory where the linked program will be loaded. On the other hand, control section address contains the starting address assigned to a control section that is currently being scanned by the loader. So this value is added to all relative addresses within the control section to convert them to actual values. We'll now look into pass 1 and pass 2 processing. During pass 1, the linking loader is specifically concerned with two record types. One is the header and define records, because pass 1 has to do with defining external symbols, and external symbols are found in header record as well as the define record. Header record specifically contains the control section name, and define record labels all external symbols that are available for program linking. So initially, the beginning address where the linked program has to be loaded, what we refer to as program address, is obtained from the operating system. This program address also becomes the starting address for the first control section in the input sequence. So control section address represents the actual start address for the control section that is currently being scanned by the loader. Further, another important variable is a control section length, which indicates the length of the control section that is currently being scanned. Generally, this information is available in the header record of the object program. So by adding the control section address for a current control section with the control section length of the current control section, we can calculate the control section address or the starting address for the next control section. So during the pass one, control section name from the header record is initially entered into the external symbol table with the value control section address. As I mentioned, control section address represents a starting address for a control section that is currently being scanned by the loader. So initially, when the header record is read, the name of the control section will be entered into the external symbol table with the value control section address. Likewise, all external symbols that appear in the defined record for a control section are also entered into the external symbol table, and their values are available. The relative values of external symbols are available in the defined record. So actual values or actual addresses of external symbols that are in the defined record are obtained by adding to the value that is in the defined record the control section address. So actual value of an external symbol is obtained by adding to the value that is available in the defined record the control section address. So when the end record is read, the length of the control section is added to the control section address to obtain the starting address for the next control section, or to obtain the control section address for the next control section. So in pass 1, to summarize, name of the control section from the header record is entered into the external symbol table with the value control section address, CSADDR. Further, all symbols in the defined record are entered into the external symbol table with the value that is currently available in the defined record plus the control section address. When the end record is encountered during pass 1, the control section length, which is actually available in the header record and saved in the variable CS length, is added to the control section address to obtain the starting address for the next control section in the input sequence. So you may notice that during pass 1 only the header, define and end records are processed, while the text and the modification records are ignored. By the end of pass 1, external symbol table contains all external symbols defined in the set of control sections together with the address assigned to each of the symbol. Further, loaders include as an option the ability to print what is known as a load map, which shows each of these external symbols along with the assigned addresses. We will now consider pass 1 processing of linking and relocating loader and see how the external symbol table is created for the set of object programs for program A, program B, and program C, which we have considered in the earlier discussion. So these are the 3 object programs generated. Let us assume that the control sections are given to the linking and relocating loader in the order program A followed by program B followed by program C. So processing begins with the first record in the input sequence, which is a header record for program A. As you see, it specifies the name, starting address, and the length. Length of the control section is saved in the variable CS length. Before storing the symbols, initially, the initial load address from where the linked program is loaded into memory needs to be fetched. So let us assume that the beginning address where the linked program is loaded into memory is 4000. So this address also becomes the starting address for the first control section, that is program A. So program address is 4000 and CSADTR, that is a control section address for the currently scanned control section, that is program A, is 4000 as well. So when the header record is processed, the name of the control section will be entered into the external symbol table. Name is program A with the value. Value is in the control section, the value is 0, but this is a relative address assumed for assembly purpose. So actual value now can be obtained by adding to this the control section address for program A. So 0 plus the control section address for program A is 4000, which is 4000, which will be entered into the external symbol table along with the length. The next record processed is a defined record, which labels two external symbols, list A and end A. You may see that the relative values of these symbols are 40 and 54 respectively. So these symbols are again stored in the symbol table by calculating the actual address, adding the control section address to the values indicated here. So the first symbol in the defined record is list A, which is entered into the external symbol table with the value 40 plus the starting address for program A, which is 4000. So 4040 will be entered into the external symbol table. You see that in program A, we have in the defined record the first external symbol list A, which is being entered into the symbol table with the value 40, which was indicated in the defined record 40, plus the control section address for program A, which is 4000. So 4040 is entered. Thereafter, the second symbol, external symbol is red, which is NA, and it is entered into the symbol table with the value 54 plus the starting address for program A, which is, sorry, it should be 54 here. So 54 plus the starting address for control section A, which is 4054. Thereafter, the remaining records are processed one after the other. You may see that the rest of the records are the refer record, text record, modification record, and so on. These records are generally ignored during pass 1 processing, as pass 1 has to do only with defining symbols. So finally when the end record is encountered, the loader estimates the starting address for the next control section in the input sequence by adding the current control section address with the control section length for the control section that is currently scanned. So we know that the control section address for program A is 4000 and the length is 63, which is available in the variable CS length. So by adding these two, we get the starting address for the next control section in the input sequence, which is program B. So CSADDR for program B is 4063. Next, after the end record of program A, we have in the input sequence the header record for program B. So now again, since we have an external symbol here, this has to be entered into the symbol table along with the actual address of program B. So the relative value for program B is 0. So actual value is obtained by adding to this the starting address for program B, which was earlier estimated as 4063. So you may see that program B is entered into the external symbol table with the value 0 plus the starting address for program B, which is 4063. So 4063 is entered into the symbol table, external symbol table. Also, the length that is available in the header record will be saved in the variable CS length, because this is required to estimate the starting address for the next section. So you may see that the value is also saved in the external symbol table in the length field. So once the header record is processed, thereafter the defined records are processed. So here you may see that the defined record labels two external symbols, list B and NB. So the first symbol list B will be entered into the external symbol table with the value 60 plus the starting address for program B. So 60 plus the starting address for program B is 4063. So 60 plus 4063 is 40C3. This is entered into the external symbol table. We have one more symbol, that is NB, and its relative value is 70. So the actual value is calculated as 70 plus the starting address for program B. So 70 plus starting address is 4063. So the value of NB that is saved in the symbol table is 40D3. So after that, remaining records are processed. However, they are not, they are simply ignored. And finally, when the end record is encountered, the beginning address for the third control section, that is program C, is estimated by adding the current control section address for program B plus the current control section length. So 4063 plus 007F will give the starting address for program C. You may see that 4063 plus 7F is 4082. Now this is the control section address for program C. So after the end record for program B is processed, the next record in the input sequence is read, which is the header record for program C. So when the header record is processed, the name of the control section will be entered along with the value. Value is estimated as the value in the header record plus the starting address for program C. So you know that program C has a starting address 40E2. So the control section name program C from the header record will be moved into the external symbol table with the value 0 plus 4082, which is 4082. Further, the length of the control section for program C, which is 51, is saved in the variable CS length. Also, it is entered into the external symbol table. Thereafter, the next record is processed, which is the defined record, and it labels two symbols here. One is list C and end C. Relative values are 30 and 42. So these two symbols are also entered into the external symbol table with the actual value estimated as 30 plus the starting address for program C. So list C is added with the value 30 plus the starting address for program C, which is 4082, which is 4112. Likewise, NC is entered with the value 42 plus 4082, which is the starting address for program C. So 4124 is a value, actual value for NC, which is entered. The rest of the records are processed and ignored. Finally, when the end record is encountered, the starting address for the next control section could be estimated if there is any. So it is estimated as 51 plus the current control section address 4408 to 4133. However, in our case, we had only three control sections. So it means that the end record here indicates the end of the input. So by the end of the input is reached, pass one processing is complete and the external symbol table is created with all external symbol table symbols entered with their actual addresses. Now we are ready to look into the pass 2 of the linking loader. So pass 2 has to do with the actual loading, relocation and linking. Hence, the major records that are processed here are the text and the modification records. So pass 2 is mainly concerned with processing of the text and modification records. So when the text records, you know the text record contains translated instructions and data, while modification records indicates the relocation information as well as the linking information. So when the text record is read, the object codes in the text record is moved to the specified address. However, the value that is specified in the text record is only a relative value. So the actual location where the object codes are to be moved is estimated by adding to the specified address the control section address. Likewise, when the modification record is encountered, the symbol whose value is to be used for modification is first examined or searched in the external symbol table, and then its value is used in adding or subtracting from the location or from the indicated location in the memory to do the necessary linking or relocation. So we will now specifically examine the pass 2 of the linking and relocating loader and see how reference 4 explicitly is processed and how the values are loaded into the memory uh, by a linking and relocating loader. So although I'll be considering only reference 4, the same mechanism will be employed in loading any other object code into the memory. So we will first consider, let us examine what is reference 4. You may see that reference 4 represents reference to the external symbol where the operand indicates the values of data words. Earlier in our discussion during part 1 of the video, I have mentioned that reference 1 through 3 corresponds to instruction operands, while reference 4 through 8 are values of data words. So I'm considering reference 4 here, which represents values of data words. And you may see that the initial code generated is 1 4 in program A, which is estimated as NA minus list A, with one modification record indicating that value of list A to be added. So you may see that the data is generated at the location, relative location 5 4. So at the location 5 4, we have the initial code 1 4. Also, since list C is not known in program A, one modification record was generated saying that value of list C should be added at the address to get the final value, because 1 4 is not the final value, it is just NA minus list A. List C should be added, and this will be done at the time of loading. So this is the object program for program A. So I'm specifically considering how the data is loaded and how the linking is performed by the linking loader corresponding to reference 4. So when the text record is processed by the linking loader, it initially moves the object code 1 4 into the memory location 5 4 plus the starting address for program A. So we have assumed that for, okay, this is a object program. The length of the program A is 63. Name is, sorry, the starting address, relative address is 0. And we have assumed that the beginning address where the linked program is stored is 4000. So that way the starting address for program A is also 4000. So when the text record is processed, the code 000014, which corresponds to reference 4, will be loaded into the memory at the address that is indicated in the text record plus the starting address for program A. This is program A. So starting address for program A has to be added, and in that location the code 14 will be moved into the memory. So we know that the starting address for program A is 4000. So at the location 4000 plus 54, the code will be moved into memory. So the indicated location is 4054, and here you may see that 000014 is loaded. But that is not complete because 14 is only and is the estimated value at the assembly time, but the actual value can be obtained only by adding the value of list C. So getting back to the source program, you may see that reference 4 is estimated as NA minus list A plus list C. We had only estimated NA minus list A. List C is not known at the assembly time. So we will see now how the linker, the linking and locating loader adds the value of list C and places the actual value into the memory location. So we have just seen that at the location 4054, 14 has been loaded when the text record is processed. Later, when the modification record is processed, the value of list C has to be added at the same location, at the indicated location, plus the starting address for programming. So the modification record says that at the location 54, add the value of list C. But this 54 is a relative value, so we need to get the actual value where list C has to be added by adding the starting address for program A. Starting address for program is 4000. So 4000 plus 54 is 4054. At this location, value of list C has to be added. But where is this value available? Please note that this value was available in the object program in the defined record for program C. And list C had a relative value 30. And during the pass1 processing, we had estimated the actual value of list C as 4112, which is the relative value 30 plus the starting address for program C, which is 4082. So the actual value of list C was 4112. So this value has to be added. So currently At the location 4054, we have 000014 from the text record, and from the program C, value for list C was entered into the symbol table during pass 1, which is 30 plus the starting address for program C, that is 4082, and the resultant value of list C, actual value of list C was 4112, which is 30 plus 4082. So now this value needs to be added, because in program A we have a modification record saying that to the relative value 54, to the relative value, sorry, to the value at the relative location 54, add the value of list C. So earlier it contained 0014. To this location now the value of list C has to be added. List C is value of list C as of now is 4112. So this is added to the data that was earlier present in the location 4054, which is 0014. So 4112 is added to 0014 to get the result 4126. So you may see it in one shot here. So program A specifies that 14 has to be loaded at the address 54, but this 54 is a relative value. So actual location where the loading has to be done is 54 plus the starting address for program A, that is 4000. So 4000 plus 54 is 4054. So you may see that this is a location. In this location, initially we had 0014 from the text record. So it is initially loaded from the text record at the location 4054, but then the modification record says that to the same location add the value of list C. From the object program for list C, the relative value for list C is 30, and its actual value is estimated by adding the starting address for program C, which is 30 plus 4082. So actual value for list C is 4112. So 4112 should be added at the address 54 plus the starting address for program, that is 4054. So initially it had the value 0014. Now when we add the value of list C, that is 4112, the value loaded into the location 4054 is 4126. So this is an example of how the linking takes place, or how the loading, linking and the loading takes place, uh, specifically for reference 4 in program A. So with this example, we are now ready to look into the algorithm for the pass 1 of the linking and relocating loader. So I'm just going to summarize the things as we have already seen how it happens. Initially, program address is obtained from the operating system. Also, the program address that is fetched from the operating system serves as control section address for the first control section. So once this setting is done, records are read from the input one after the other until the end of the end of the file is reached. So when the record is read, first the header record will be read. So when the header record is read, the length of the control section that is available in the header record is saved in the variable cs length. The name of the control section in the header record is entered into the external symbol table, provided it is already not present in the symbol table. So search the control section name for in the external symbol table. If it is found, it is a duplicate symbol, external symbol. So set the error flag, else enter this control section name into the external symbol table with the value that is indicated in the header record plus the starting address for the control section. So in other words, it's same as entering the control section name with the control section address for the current control section. So after header record is processed, the next record, as long as the record is not end record, one after that the next record is fetched and checked if the record type is D. So if the record is the defined record, then for every symbol in the defined record, the linking loader examines if the symbol name is already present in the symbol table. If so, it sets the error flag. Otherwise, this external symbol in the defined record will be entered into the external symbol table with the value control section address plus indicated address. Please note this control section address needs to be added for every relative value that is indicated in the object program. So after this, the next record is processed. So all the remaining records which are not of type D will be simply ignored. Finally, and this processing continues until the end record is encountered. So when the end record is encountered, the length of the current control section is added to the starting address of the current section to get the starting address for the next control section. So next, the process is repeated again. The header record is processed, and as long as the record type is not a defined record is processed, and all the remaining records are ignored. And when the end record is encountered, the control section address is added to the control section length to obtain the starting address for the next section. The process will be repeated for every object program, and the process terminates when the end of the input is reached. That is when all the records from the input sequence has been read. So as I mentioned earlier, loaders have an ability to has option to print what is known as a load map, which labels all external symbols and their addresses, also including the length. So this is a snapshot of the load map that is created for the example that we had considered, which contained in the input three control sections: program A, program B, and program C. We will now look into the pass-to processing. As you have seen, pass-to processing has to do with processing the text record and moving the object codes at the indicated address, and doing the necessary modification by searching the external symbol indicated in the modification record in the external symbol table, and doing the modification by adding or subtracting the symbol at the indicated location. So we will first begin by fetching the program address from the operating system, and the program address becomes the control section address as in pass1 for the first control section. Also, one more variable is used, execution address. So this execution address indicates the starting address from where the execution has to start. So the load address uh, is actually referred to as program address, and execution address indicates the starting location from where the execution has to begin. So initially, the execution address is set to the program address itself. For example, in our case, we have assumed that the program address is 4000. So initially, execution address will be set to 4000 itself. So like as in pass 1, until the end of the input is reached, one after the other records are fetched, and when the header record is read, the length of the control section is saved in the variable cs length. None of the other things are done in pass 2 here, because in pass 1 the control section name was saved into the external symbol table. During pass 2, when the header record is read, only the control section length will be saved in the variable cs length. So after the header record, the remaining records are fetched one after the other, as long as the record type is not E. And it's checked if the record type is T or M. If the record type is T, then the object code which is in the character form has to be converted into internal representation, and it has to be moved from the record to the location that is specified in the text record plus the control section address. So for every object code in the text record, it is moved into the location specified address plus control section address. On the other hand, if the record type is M, then the symbol in the modification record, external symbol in the modification record, will be looked up in the external symbol table, and if it is found, its value will be fetched and it will be added or subtracted as indicated in the modification record at the location that is indicated in the modification record plus control section address. So we have already seen how this happens for reference 4, wherein the specified address is 54 and the control section address is 4000. So it's possible that the external symbol that is indicated in the modification record is not stored in the external symbol table, in which case the error has to be indicated. So this is regarding the processing of text and the modification record. So this is to be repeated for uh, every record in the object program. So each time a record is fetched, the linking loader examines if it is a header record. If so, it saves the length. If it is text record, object codes are moved into the memory at the location specified address plus the control section address. On the other hand, if the record type is M, the modifying symbol will be looked up in the external symbol table, and if it is found, its value will be added or subtracted at the specified address plus control section address. Remember that in the object program, all values are relative values. So to whatever values that are specified in the object program, always the control section address needs to be added to get the actual value. Be it with respect to processing of the header record, text record, modification record, or define record. So whenever end record is encountered, because when we have multiple control sections, end record might be encountered multiple times. So whenever the end record is encountered during pass through, the linking loader sees if the end record has an associated address following the end record. If there is an address, so if there is an address following the end record, then the execution address will be changed to the address that is indicated in the end record plus the control section address for the current control section. That is, unless explicitly specified in the end record, always the execution address will be considered as a load address, that is program load address. If end record specifies an address, then the execution address will be set to the address that is specified in the end record plus the control section address. Further, uh, since the end record indicates the end of a particular object program, the starting address for the next control section has to be obtained. So this is done by, as usual in pass 1, by adding the control section length to control section address. So this process, after this is done, the next record will be fetched in the input, and as long as it is not the end, the remaining records from the following object programs are processed one after the other, and the process is repeated until the end of the file is reached. So when the end of the file is reached, the execution has to start, because all the object programs code from the object programs would have been loaded, and the necessary resolution of external references would have been done. So when the end of the input is reached, the linking loader jumps to the location execution address to begin the execution. So that is all regarding the pass two processing of linking loader. It's to summarize, in pass one, we have seen that the header and defined records are processed and symbols are entered into the symbol table with the value indicated in the define or header record plus the control section address. Whereas in pass two, uh, major records processed are the text and the modification records. And when the text record is encountered, object codes are moved from the text record to the indicated address plus the control section address. While if the modification record is encountered, symbol is searched in the external symbol table, and the modification is done by adding the value of that symbol at the address indicated in the modification record plus control section address. Finally, when the end record is encountered, if end record specifies an address, then the value that is indicated in the end record plus control section address will be taken as the execution address. Otherwise, the initial load address itself will be assumed as the execution address. So finally, when the end of the input is reached, the loader jumps to the execution address to the location indicated by the execution address to start the execution. So I suggest that you go back and check how reference 4 is handled by the linking and relocating loader, and see how each of the references in the object program are handled, and see how what are the object codes loaded into the memory. So this is a snapshot of program A, program B, and program C loaded into the memory after linking and loading. You may see that reference 4 through reference 8 will result in the same value, because they are values of data words, while for references 1 to 3, which are instruction operands, The calculated values after loading are not necessarily same, because in one program it could specify a 4-byte format, while in other it could specify a 3-byte format. So you may see the values as loaded into the memory for reference 4 and 1. So you may see that for reference 4 all values are exactly the same, while for reference 1 it is different. In program A, it is assembled using a relative mode because all values were available. So it's a 3-byte instruction, while in program B and C, the values are different. They actually are assembled using the 4-byte or extended format, and you may see that those two are same because it involved an external reference in program B and program C. The algorithm for linking loader that we have just discussed can be made more efficient if a slight change is made in the object program format. The modification involves assigning a reference number to each external symbol that is referred to in a control section. And the reference number will be used in the modification record instead of symbol name. Suppose that we assign reference number 1 to the control section name, and other external symbols will be assigned numbers as a part of refer record of the control section. Then the same object program would be rewritten as follows. So you may see that we have assumed program A to have a reference number 1. All external symbol in the refer record will be having the successive numbers, like list B will have the number 2, and B will be having the reference number 3, and so on. And C will have the reference number 5. So wherever a reference to list B is done, in its place we use, instead of list B, the name of the symbol, we use the reference number, that is 02. So similar change has been done to program B. It has been rewritten to include the reference number mechanism. Likewise, program C has incorporated the reference number mechanism. The advantage is that it avoids multiple searches of the external symbol table for the same symbol during the loading of a control section. An external symbol table has to be searched every time a reference to a symbol is made in the modification record. As you see here, for example, list A has been referred to in some 5 to 6 places in the modification record. And each time the external symbol table needs to be searched and the value has to be fetched. So by using the reference number mechanism, an external reference symbol can be looked up in the external symbol table once for each control section that uses it. And the value for code modification as specified in the modification record can then be obtained by simply indexing into an array of these values. So you may see that we have maintained 3 arrays, one for program A, program B, and program C. And the addresses associated with each of the external symbol, which are actually now referred to by the reference numbers, are placed into the array. So whenever a reference to list B is done, it's just a matter of retrieving the second entry from the table because it is referred to in the modification record with the number 2. So that is all regarding the functionalities of linking and relocating loader. We had begun this discussion in the part 1 of the lecture, wherein the issues of program linking from the perspective of assembler was discussed, and we have seen how a program involving complex, wherein a program involving complex references were handled by assembler, and how the object program was generated. Thereafter, we have examined how linking and relocating loader processes the object program and moves the object codes into the memory after doing the necessary linking. So I have a question for you now. We have already seen how reference 4 in program A was processed by the linking and relocating loader, and we have depicted it in the form of a figure that is shown here in slide 230. So The assignment is now you need to depict the relocation and linking operations that is performed on reference 8 in program A, program B and program C as was shown for reference 4. So depict the relocation and linking operations performed on reference 8 in program A, program B as well as program C using the figure that was just shown for reference 4. Thank you.